Today I wanted to talk about work and energy. Work you can think of as an action that causes some sort of change or transfer, whether it's causing an object to speed up or maybe an object to change its shape, or even if a system of objects transfers energy from one object to the next. And then that begs the question, what is energy? Well, energy is basically a made-up number that we use to quantify an object's capacity to do work. So you can think of work as the action and energy as the cost for doing that action. So the more energy you have, the more work you could do. And work we represent with a capital W. We quantify that as the force for a certain displacement. And it's actually a dot product. So we're multiplying them together, but we really care about just the parallel components when we multiply these two together. So you may see it written as F times whatever you're using for your displacement times cosine of theta, which means maybe you're displacing something to the side and you're pushing down on the object. This angle here would be your theta. So we really only care about that sideways component of, or the sideways component of that force. And what you'll notice is that we do have a complex unit here. It's newtons dot meters. Cosine just returns a ratio of the same measurements, so there's no units there. And 1 Newton meter is equal to 1 joule. Joule. And so that's how we quantify work. Whatever action is creating that change, whatever action is transferring that change, this is one way we quantify it. For energy, we categorize it basically by how the energy is being expressed. And we have mechanical energy. Okay, where was I? Mechanical energy and non-mechanical. Typically, you can kind of distinguish between the two as mechanical is energy that we can still quickly measure or utilize, whereas non-mechanical energy is hard to get back in some form that we can use or measure. Mechanical energy we break into two categories, kinetic and potential. Kinetic is represented with a capital K. Potential is represented with a capital U. And when we talk mechanical energy or even total energy in a system, we use that capital U as well, since we're thinking of that energy as being within the system. Kinetic energy is the energy an object has due to its motion. Whereas potential energy is the energy an object has due to its location, its shape, essentially because it's existing in some way or shape or form, or it's interacting with other objects. For that reason, potential energy always requires two objects in your system. Either one to do the storing, or the other one to maybe generate a field, and we can talk about the energy being stored in that field instead, like a gravitational field or electrical field. But I want to focus today on kinetic energy. Classically, it's the only kind of energy that a single object can have because we just need one object to move. And we break that down into translational and rotational. And we're going to focus on translational today. Energy at the time of Newton was a pretty new concept, and he kind of saw it as indistinguishable from momentum. So he thought that the kinetic energy in an object was proportional to its speed. And in the early 18th century, a French mathematician and physicist by the name of Emily du Chaillet was translating his Principia to French, and she also translated with some commentaries and criticisms, and one of these was regarding Newton's thoughts for energy. She remembered a experiment by the Dutch scientist Wilhelm Gravesund. Am I saying that right? Basically, his experiment involved taking a lead ball and dropping it onto some clay. And thanks to the work by people like Galileo, we could actually figure out the impact speed. And he related the impact speed to basically how much penetration there was in the clay. And this goes back to what I was talking about, work and energy, how they relate. By placing it higher, gravity can do work on the ball and give it more speed. Well, now that the ball has more speed, it has energy, kinetic energy in this case, and it can do work on the clay, deforming the clay. And Du Châtelet repeated this experiment and found that by changing the height, when she doubled the impact speed, the penetration into the clay was quadrupled. Tripling the speed made the penetration, the depth go up by 9, not 3 times. So her commentary was that perhaps Newton was wrong about energy, that it wasn't proportional to the speed, but the speed squared. And this would later lay the groundwork for what we know about energy for people like Euler and Lagrange. And today we know kinetic energy as 1/2 mass times the speed squared. And that's for translational energy, for an object that is translating from point A to point B. Excuse me. And you can see here, if we look at the units, we can break these up into kilograms, meters per second squared, times meters. And we see that kinetic energy would be measured in joules. In fact, all forms of energy are going to be measured in joules. So the question is, we know that work and energy are related through these units and through the action cost that I was talking about. In the next video, we're going to look at how that happens.